Assalamu alaikum, dear students. Welcome to the course Principle in Animal Life 1. This is lecture number 37. The topic is the pH scale. Discussing agenda for the topic will be acids, bases, and the pH scale. Lecture outcome. After watching and listening this lecture, students will know about pH scale and pH values of different substances. Introduction. We have already discussed acids and bases in a separate lecture, but here we are discussing pH scale. Therefore, we will shortly revisit this topic and discuss acids and bases again. So when acids dissolve in water, they donate additional hydrogen ions to the solution. Now pure water has equal concentration of hydrogen and hydroxyl ions. Sometimes the water molecule dissociate into hydrogen and hydroxyl ions. So in a pure water there is equal number of hydrogen and hydroxyl ions, and we refer to this situation as having a neutral pH or 7. So when acid is added to a solution which has a neutral pH or to a pure water, what will happen? The acid will donate additional hydrogen ions to the solution. So the population of hydrogen ions will increase in comparison to the hydroxyl ions, and that solution or the water will become acidic. So what is an acid? An acid is a substance that increases the hydrogen ion concentration of a solution. You can also define an acid as a substance that decreases the hydroxyl ion concentration of a solution. Now, hydrochloric acid is the example of an acid. It is a strong acid. It is found in the stomach, having a pH of 2 there. So when HCl is added to water, it dissociates into hydrogen ions and chloride ions, as shown by this chemical reaction. Now this single arrow means that this dissociation is complete. There is complete dissociation of HCl into its ions, and such an acid which is dissociated completely is known as a strong acid. And whenever you see a reversible reaction, then it refers to an acid which is a weak acid which dissociates partially. So this source of hydrogen ions dissociation of water is the other source, results in an acidic solution. So one source of hydrogen ions in a solution is obviously when an acidic solution is added, and another source of hydrogen ions is the dissociation of water molecule. So now base. What is base? A base is a substance that reduces the hydrogen ion concentration of a solution, or in other words, a base is a substance which increases the hydroxyl ion concentration of a solution. So you can use two definitions both for acid and base. Now, some bases reduce the hydrogen ion concentration directly by accepting hydrogen ions. So, because these bases dissociate and their dissociation products combines with the hydrogen ions, thereby decreasing the population of hydrogen ions and increasing the basicity. For example, ammonia. Ammonia acts as a base when the unshared electron pair in nitrogen's valence shell attracts a hydrogen ion from the solution. Now, this hydrogen ion, it is simply a proton. It doesn't have an electron. So, when ammonia is added to a solution, the unshared electron pairs attracts a hydrogen from the solution, and the result is ammonium ion. So the addition of ammonia resulted in the decrease in the population of free hydrogen ions because some of the hydrogen ions were bound to ammonia to form ammonium ions. So in this way, the population of hydrogen ions decreased, and because we use these two ions, we compare these two ions when we talk about acidity and basicity. So if the concentration of one ion decreases, then automatically the concentration of another ion or the hydroxyl ion increases. Now here you can see, but here you can see a reversible reaction. So it means that this ammonium ion which is formed, it can undergo a reversible reaction and once again dissociate into ammonia and hydrogen ions. So this reversible reaction shows that this dissociation is partial. So ammonia is a weak base. Other bases reduce the hydrogen ion concentration indirectly by dissociating to form hydroxide ions, which combine with hydrogen ions and form water. So this was a direct decrease in the population of hydrogen ions. Now here the population of hydroxyl ions increases, so in comparison to the hydrogen ions. So what will happen? The basicity of the solution will rise. So the rise in basicity of a solution is ensured in two ways. First, either decrease the population of hydrogen ions or increase the population of hydroxyl ions. In either case, the base reduces the hydrogen ion concentration. Here it bound with hydrogen ions, the population of free hydrogen ions decreased, and here it produced hydroxyl ions, so the number of hydroxyl ions increased in comparison to the hydrogen ions. Now, solution with a higher concentration of hydroxyl than hydrogen are known as basic solutions, because the hydrogen and hydroxyl ion concentration of pure water is equal. Therefore, the pH of pure water is 7. So, when the concentration of hydroxyl ions is greater, then the solution is basic. When the concentration of hydrogen ions is greater, then the solution is acidic. When the concentration of both of them is equal, the solution is neutral. So a solution in which the hydrogen and hydroxyl ion concentrations are equal is said to be neutral, having a pH of 7 like pure water. Notice that single arrows were used in reactions of HCl and NaOH because this is a strong acid, this is a strong base, and why they are termed as strong acid or base, because of their ability to dissociate. A strong base or a strong acid dissociate completely, a weak base or a weak acid dissociate partially. So these compounds dissociate completely when mixed with water. So hydrochloric acid is called a strong acid and sodium hydroxide a strong base. In contrast, you saw a double arrow in the reaction where ammonia combined with hydrogen ions to form ammonium ions. This double arrow indicates or refers to the fact that this reaction is reversible and this dissociation is partial. The double arrow in the reaction for ammonia indicate that the binding and release of hydrogen ions are reversible reactions. Although at equilibrium there will be a fixed ratio of ammonium ion and ammonia. So obviously when dynamic equilibrium establishes, a dynamic equilibrium is one when the rate of the forward and the rate of the backward reaction is equal, and in such circumstances the concentration of the products and reactants are always also equal. So weak acids are acids that reversibly release and accept back hydrogen ions. An example is carbonic acid. Carbonic acid is a weak acid as indicated by this double arrow. It's a reversible reaction. It dissociates into hydrogen ions and then the hydrogen ions can combine with the bicarbonate and form carbonic acid again. Here the equilibrium so favors the reaction in the left direction that when carbonic acid is added to pure water, only 1% of the molecules are dissociated at any particular time. So because the dissociation is extremely low, therefore it is referred to as a weak base acid. Still there is enough to shift the balance of hydrogen and hydroxyl ions from neutrality, although the dissociation is extremely small, but it still brings some change in the concentration of hydrogen ions in comparison to hydroxyl ions, and the solution becomes acidic. Now the pH scale. The pH scale usually refers to the power of hydrogen, as the pH indicates. It's a term which is derived from a phrase Poisson the hydrogen, means the power of hydrogen. So this scale indicates the acidity or basicity of a solution. In any aqueous solution at 25 degrees centigrade, I hope you remember that usually the room temperature is referred to as 25 degrees centigrade. So in any aqueous solution at this temperature, the product of hydrogen and hydroxyl ions is constant at 10 raised to the power minus 14. So it means that hydrogen and hydroxyl ions are in equal concentration, or if they are not in equal concentration, then their overall product will be always 10 raised to the power minus 14. and this can be written as hydrogen ions, hydroxyl ions, and it will always be equal to 10 raised to the power minus 14, although there will be differences in the individual pH values, but their combination will always be equal to 10 raised to the power minus 14. As previously mentioned, in a neutral solution at 25 degrees centigrade, hydrogen is 10 raised to the power minus 7, hydroxyl is 10 raised to the power minus 7 too. So it means equal concentration of hydrogen and hydroxyl ions, and the pH is neutral or 7. Therefore, the product of hydrogen and hydroxyl is a neutral solution at 25 degrees centigrade is 10 raised to the power minus 14. A neutral solution is one where the hydrogen and hydroxyl concentration is equal. Both are having 10 raised to the power minus 7, and their addition sum is 10 raised to the power minus 14. If enough acid is added, now if acid is added, then obviously it will increase the hydrogen ion concentration of the solution, and then subsequently the hydroxyl ion concentration will decrease to an equivalent value. For example, if acid was added, then the concentration of hydrogen ions will increase, and in comparison the same decrease will occur in the concentration of hydroxyl ions. So you can see here, remember this, their product will always be equal to 7, although there will be differences in their individual values. Just like here, the solution is acidic one, the pH value, the hydrogen ion concentration is 10 raised to the power minus 5, hydroxyl ion concentration is 10 raised to the power minus 9, and their product is 10 raised to the power minus 14. So this constant relationship expresses the behavior of acids and bases in an aqueous solution. So when the acidity of a solution increases to a certain level, there will be a decrease in the basicity of a solution in the same way. Similarly, if the basicity of a solution increases, there will be a same decrease in the acidity of a solution. Now, an acid not only adds hydrogen ions to solution, but also removes hydroxide ions because of the tendency for hydrogen to combine with hydroxyl forming water. So we have already discussed that an acid either directly increases the concentration of hydrogen ions or indirectly increases the concentration of hydrogen ions by decreasing the concentration of hydroxyl ions. A base has the opposite effect, increasing the concentration of hydroxyl ions or reducing the concentration of hydrogen ions. If enough of a base is added to raise the hydroxyl ion concentration to 10 raised to the power minus 4 moles, then it will cause the hydrogen ion concentration to drop to 10 raised to the power minus 10. As already stated, that an increase in the hydrogen ions will brought a decrease to the same value in the concentration of hydroxyl ions. So whenever we know the concentration of either hydrogen or hydroxyl ions in an aqueous solution, we can deduce the concentration of the other ion. So because the product of hydrogen and hydroxyl in a solution at 25 degrees centigrade is always equal to 10 raised to the power minus 14. So if you know the concentration of either hydrogen ions or hydroxyl ions, then you can calculate the value of the other, because their product is equal to 10 raised to the power minus 14. So if you know the value of either of them, the value of the other can be calculated. Now the pH scale is a simple numerical method for expressing the range of hydrogen ions concentration. The hydrogen ion concentration of a solution can vary by a factor of 100 trillion or more. Instead of using moles per liter, the pH scale compress the range of hydrogen ion concentration by employing logarithms. So here we usually express this power in the value of something put on as a superscript on 10. The pH of a solution is defined as the negative logarithm base 10 of the hydrogen ion concentration. So this is the way how the pH value is calculated. For a neutral solution, neutral aqueous solution, the hydrogen ions concentration is 10 raised to the power minus 7 m, giving us minus log 10 raised to the power 7. So here you will mention the hydrogen ion concentration, and then the product of this equation will be 7. Now notice that the pH decreases as hydrogen ion concentration increases. So this is something which quite often puzzle the students, that when the value is increasing, we say that basicity is increasing, but on the other hand, when the value is decreasing, we say that acidity is increasing. For example, a solution having a pH of 6 is less acidic than a solution having a pH of 3. So what is the mystery behind that? That although the pH scale is based on hydrogen ion concentration, it also implies hydroxyl ion concentration. A solution of pH 10 has a hydrogen ion concentration of 10 raised to the power minus 10 and a hydroxide ion concentration of 10 raised to the power minus 4. So the pH of a neutral aqueous solution is at 25 degrees centigrade is 7, which is the midpoint of the pH scale. A pH value less than 7 denotes acidic solution. The lower the number, the more acidic the solution. The pH for basic solution is above 7. Most biological fluids such as blood and saliva are within the range of 6 to 8 pH. There are a few exceptions, however. For example, the gastric juices which are present in our stomach, they have a pH of 2. Remember that each pH unit represents a tenfold increase in hydrogen and hydroxyline concentration. So if the pH is 3 and it drops to 2, then there will be a tenfold increase in the concentration of hydrogen ions. Similarly, if the pH drops from 2 to 1, there will also be a tenfold, a 10 times increase in the concentration of hydrogen ions. It is this mathematical feature that makes the pH scale so compact. So a solution of pH 3 is not twice as acidic as solution of pH 6, but 1000 times, because there is a tenfold increase or decrease in acidity. When the pH of a solution changes slightly, the actual concentration of hydrogen and hydroxyl ions in the solution changes substantially, because a small change in the pH have a drastic effect on the concentration of hydrogen and hydroxyl ions. Now on the right side of your figure you can see the pH scale. This shows the acidic environment or the acidity values. This shows the basicity values, and this is the neutral point where the concentration of hydrogen and hydroxyl ions is equal. Here in the acidic portion, concentration of hydrogen ions is greater. Here concentration of hydroxyl ions is greater, and then you have these values. So the pH of vinegar and wine and cola is 3, and that of tomato juice, beer, is 4. The urine is 6, pure water is 7, the human blood has 7.4, the seawater has 8, milk of magnesia has round about 10 to the power 10.5. So this shows different pH values. And remember the buffer system, carbonic acid bicarbonate buffer system, which is present in the blood, which neutralizes any changes in the pH values upon the addition of an acid or base. This is the book from which the material was taken. You can also refer to this book. Thank you very much. Allah Hafiz.